Hello Year 10, this is Mr. Tickner, and this is a video to work through the end of year exam that you can watch. There are links to each individual questions in the description, and let me know if there's anything that you need any extra clarification on. So, working through it. Question 1, a nice straightforward recall one, so it's all about remembering a formula and using it. State the formula linking density, mass, and volume. In words or symbols, density is equal to mass over volume. If you want to do it in symbols, the symbol for density is a curly P, it's a rho, so rho is M over V. You were allowed to use a D, but sometimes you're not given it. But in this one, it did say condone the use of D for density. But the symbol you should be using is a rho. Then it's just using it. So marks here. The first mark is for either subbing in or rearranging. So either, so we can put in our numbers. So the 8.46 is equal to 4 over V. So then we can rearrange that. V would equal 454 over 8.46, and so we rearrange it in the second marker to the evaluation. We get V is equal to 53.7. What's the unit? Well, because we're in grams per centimeter cubed, we're going to get or cubic centimeters. Sorry, we are going to get an answer in cubic centimeters. You don't need to convert to cubic meters because it's been given to you in cubic centimeters. It's perfectly fine, but 53.7 cubic centimeters. Okay, there were no marks for your significant figures on this one. Right, question 2. Question about atmospheric optical illusions. So we've got a mirage. We've got a diagram of how a mirage is formed. Due to total internal reflection between cold and hot air, and state the formula linking critical angle and refractive index. So sine C is equal to 1 over n, where n is the refractive index. That's fine in either order. Critical angle of the cold air boundary is 88.500 degrees. So we've got our critical angle, calculate the refractive index, give your answer to 5 significant figures. There is a mark for substitution, a mark for rearrangement, and a correct evaluation. So if we would say sine of 88.500 equals 1 over n. So we end up with n is 1 over. So n equals 1 over sine of 88.500. Sorry, my pen is being a bit weird. Okay. 0. And this gives us a value of n to 5 significant figures of 1.0003. If you go further than this, so for example, the next digit is a 4. If you wrote that next digit or any others, you would lose a mark. So that's your 5 significant figure answer. So of B, we've got the ray of light from the sun. We've got the refractive index is greater. Complete the diagram by drawing the path of the ray of light through the atmosphere. So the ray of light from the sun, we know that it's going to enter something that's denser. It's going to slow down. So we are after a straight line because it's still going to stay straight. I don't have a ruler function, but I'm going to try my best. There we go. So some straight line. Oh, that's exciting. Okay, let's get some arrows on that. Don't quite know why it did that, but there we go. So it's got a bend towards the normal, and it's a straight line. So 1 mark for there being a straight line. Anyway, even if you drew it going up that way, you get 1 mark. But 1 mark for it being a straight line that is above the normal line. The second mark is that it is in this sort of region that's clearly bent towards it. Okay. So diagram 3. Why is he doing this? So let's. So we've got a ray of light that shows ray of light from the sun is directly overhead. Explain why the ray of light does not change direction when it enters the atmosphere. So what we need to have here is when a ray of light goes from a less dense to a more dense, or it slows down, it should bend towards the normal. However, it can't bend towards the normal because it's already on the normal. So it's asking you to sort of give an idea that's along those sort of lines. So so your first mark is for saying that the angle of incidence is equal to 0, or it's his ray is traveling along the normal, okay, or at 90 degrees, or all the other things that it could be, and because of this condition here, that means that the angle of refraction is also equal to 0. Okay, so or saying angle of incidence and angle of refraction are equal in this particular special case. But you can't bend closer to the normal when you're already on it. So that's where it has to be. Explain why the wavelength of light reduces when it enters the atmosphere. So there are 3 possible marking points to sort of get this idea. So why does it reduce? Well, the first marking point is for a reference, so refer to V equals F lambda. Okay, so we have this equation. Speed is equal to frequency times wavelength for a wave. And in this case, what we've got is we know that as it goes into the atmosphere, it's going to slow down. We know that V is going to decrease. So our second possible marking point is that the speed speed's going to go down. And because speed is going to go down, well, that means something on this side also has to go down. And frequency remains constant. So when things move into somewhere where they slow down, frequency is actually a thing that stays the same. So if the speed goes down, the wavelength must go down because frequency is the thing that remains constant. So any of these 3 points, so if there's a reference to the V equals F lambda equation, saying the speed goes down and the frequency remains constant, any 3 of those to get the 2 marks. Right, okay, next one is suggest why the sun appears not to be circular when it is close to the horizon at sunset. Now this, I'm going to start, this is not an easy question, but it is only worth 1 mark. So I've actually imported a diagram here to sort of help explain it. So this is what is happening to the sun at sunset, okay? You have to consider the fact that the sun is an object with a size, it's a defined star size. I don't recommend you go and directly look at it to measure it, but because it's quite bright. And what will happen is that as it dips towards the horizon, it's sort of coming into you at quite a sharp angle, angle. And a ray from the top is going to refract by a certain amount, whereas a ray from the bottom of the sun is going to refract by a different amount when it hits the atmosphere. So bits from the sun, the top and bottom of the sun, refract by different amounts because when they hit this thing here, this angle and this angle are not the same. Okay, so this angle is actually bigger. So this is an exaggerated version. So they refract by different amounts, and what that leads to is a sun that appears a bit compressed. So it's quite tricky because you've got to visualize what's going on, and it's not something you can see if you think entirely of there only ever being 1 ray of light. So what they gave credit for here is that light from top or the bottom of the sun refract by different amounts. Okay, so that's the total answer they want. They did, however, also accept that, just saying that refraction as a feature gets bigger as things approach the horizon. So light from the sun will be refracted more when it's here than when it's directly overhead. Okay, so the other possible sort of marking point that was allowed is that just without even making a reference to this top and bottom thing, is that light refracts more when close to the horizon. As the angle of incidence increases. So we end up moving, so rays of light will move further away from the normal as you move sort of in this direction. Okay, so it starts off with an angle of incidence of 0, but as the sun moves across the sky, the angle of incidence is going to go up. That's a tricky one to visualize. It's not necessarily immediately obvious the best way to approach it, but again, that's why it's only worth 1 mark. Okay, so question 3. So student investigates the speed of sound in air. The student sets up 2 microphones, A and B, as shown in diagram 1. The microphones are connected to a data logger. Sound is made to the left of the microphone. So you hopefully would have seen some of this, with a wooden clapper. And we didn't use a data logger, we used a fast timer that could measure a time. But same idea, but you record the time it takes for something to go from here to there. Describe how the student could determine the speed of sound in air using their calculated value of the time taken. So the time value is already taken, it's already part of the thing. So what do we need to do? We need to, firstly, we need to measure the distance. Okay, which loads of people said that. What was said less commonly, I'd say less rarely, is what you're measuring it with. Measure it with a ruler. Okay, and then the third marking point is to say then to use speed is equal to distance over time. I read a lot of responses where this was being described in just fully in words, in entire sentences. You would take the value of distance and divide it by the value of time. You don't need to say that. You can just say use speed as distance over time, or just use the equation. You don't need to explain in a long sentence what the equation is. So you don't get more marks for making it, for spreading it out. So those are the 3 marking points. It's a bit mean. They could have said there are things to do. Suggest why the student does not use a stop clock in this investigation. So the idea here has to be basically is reaction time is too big. So some idea about the reaction time of the student being a problem, because the reaction time is too big, because the time is very small. Okay, so an idea there. A lot of responses on the way of saying things like human error, or to make it more accurate, or even sometimes, there were 2 people who said, oh, because they've already got the data logger which is measuring time. It's asking you what would be the problem if you were to use a stop clock, and the answer here is it's a problem because your reaction time would be the problem, which is a source of human error, but just a blank statement of human error isn't detailed enough. Okay, so you need to say exactly what it is. You very rarely will get a mark for just saying human error. Okay, humans, yeah. Okay, right. Okay, now the investigation's changed somewhat. We've got some Bunsen burners that are burning things, burning gas, things. On a low flame, measure the air temperature in 3 places. Use the data log to report time. 70%. Student repeats this method as the air temperature increases. Suggest why it is important for all the Bunsen burners to burn the same amount of gas each time. So what you need is you need the same temperature. You need the temperature to be kind of constant as if the sound wave is traveling across. So you don't want it to be really hot over here and cooler over here. There were some erroneous references to things like just make sure that there's the same heat. Be very careful about using the word heat. Remember the difference between heat and temperature and thermal energy. We don't really use the word heat in GCSE very much. Also, much like the last thing, in the way the human error doesn't get a mark, just saying fair test is also again not a specific enough response. Okay, so why would it not be a fair test is not a thing. So you need the temperature to be the same. So you can't just say it because it isn't a fair test. Right. Okay. Then we have a table of results. And we have to calculate a mean, give your answer to a suitable number of decimal places. Now there is a big clue in that all the numbers here, all of them in this sort of sensor area, they are all to 1 decimal place. And all the averages or the means are to 1 decimal place. So there were a lot of people who didn't like that and wanted to write 4, but everything in this table is screaming at you 1 decimal place. So pay attention to what you're being given. So you're doing the average of this number, and this number. So you end up with 59.97, which would round to 60.0 if you're only going to 1 decimal place. So if you correctly get 59.97, you get 1 mark. If you then actually turn it to 60.0, you get the 2nd mark. So there's a reason that they put 60.0 because you have to do a bit of rounding. Cool. Right. Okay. The student plots his results, draws the line of best fit, draw a circle around the anomalous result. This was actually missed, and I'm sure those of you who fell into that trap probably quite frustrated. Literally just, I didn't even do it in red. That one. Yeah, and I think because it was just at the top, people just sort of missed that there was a question there. So just be careful when you're doing questions that that you do check that there's nothing at the top. State how the student should deal with the anomalous results. They should ignore it, or discard it, or repeat it. Okay, so if something looks wrong, then you would either disregard it or ignore it. So they've ignored it when they've drawn their line of best fit. Right. Explain why a line graph is the correct type of graph to display these results. This is a question people struggled with. So what is it that's there? Why do we use line graphs and not bar charts? It's for when data is what we call continuous. So there is an entire continuous line that goes from 20 to 70. Okay, so you could have any value between 20 to 70. You keep going that way. But you can smoothly go this way and you can smoothly go that way. So, so essentially for 2 marks, you can say that, the data is continuous. Okay, so continuous data is just numbers that can smoothly move across. Discontinuous data or discrete data might be if you are trying to measure, you're trying to count the color of cars as they drive down a road. They're either blue or red or yellow. You don't end up with this sort of I guess someone could have a stripy car, but generally you just have this kind of they are discrete things. So we use line charts or line graphs when the data is continuous. We'd use a bar chart if you're just comparing discrete things that would have no sort of like smooth transition from one to the other. Describe the relationship between the speed of sound in air and in temperature. So what we have here is that first, most people got is that as not as speed increases, sorry, the other one, other way around. So as temperature increases, then speed increases. And this was very commonly said, and this obviously gets you 1 mark. But this is a 2-mark question. So what else can we say? The relationship is linear. People were a bit vague when they said like it goes up evenly or it goes up at a continuous rate. A second point was not added too much, but you are off that. Now this is not a proportional relationship. A proportional relationship would go through the origin, and there is no way that this is going to go through 0, 0, because on here we're at 344 and here we're at 20. So this is not a proportional relationship. So just be aware that a linear relationship is mathematically y equals mx plus c. There is going to be some instance. Proportional is just y equals mx. So that would go through. That goes through 0, 0. This doesn't. This is not going through 0, 0. It is not proportional. It is a linear relationship. So the mark scheme was said reject if you talk about it being proportional. So this, just be aware of the difference between the two things and when to use the term in physics. Again, physics exams do not tend to really reward the phrase positive correlation on its own. It's asking you to be explicit about what is the relation between the two variables. So be a bit clearer. Cool. Okay, question 4. This diagram shows. So we've got a bit of an electricity question. Give the name of this component. This component is an LDR, or a light dependent resistor. The voltage across component X is 3. So calculate the voltage across 4,500. So let's think about what this would mean. We have a 12-volt battery. We have 3 volts here. So therefore, how much do we have here? Well, voltage in series splits. So if we use 3 here, we would need 9 there. So that's 9 volts. State the relationship between current, voltage, and resistance. Voltage is equal to current times resistance. In words or in any order. Calculate the current in the circuit. Now, here, several people then went back and said, I'm going to use V as 12. But you use V equals IR over a component. So I've been looking at, we've got a 4,500 ohm resistor, and we know we've got 9 volts across it. Okay, so what we're looking at is what's going on here in the circuit. Because it's a series circuit, we're going to have the same effect here and here, but we have to use the voltages across the component. So we would have, for this one, substitution or rearrangement is our thing. So we've got current is equal to voltage over resistance. So we've got 9 over 4,500, which gives us 0.002. If you use 12, then you get 0.0027, or some people round it to 0.003, which you get 1 mark. But you want to be using 9, not 12. Calculate the resistance of component X. Give your answer in kiloohms. So we're using the same equation again. Okay, but this time we've got the current and we've got the voltage. So we want to use this number. We want to use this number and this number now. Okay, so we are then going to use go back to using V equals IR again, just so we have 3 equals 0.002 times R, and that gives us the value of R is equal to 1,500 ohms. Convert that to kilo ohms, divide by 1,000, 1.5 kilo ohms. Okay. Now, just be aware when marking this, there was a lot of things called, you might see a thing called ECF, that was error carried forward. That's if you use this number here, so you made the mistake in what the current was, but you used it correctly. I think if you use 0.0026 or 27, you end up with something like 11, somewhere in the region of 1100, I think. If you round it to 0.003, you end up with 1,000. So you could get error carried forwards. Also, for others who made a bit of a mistake, you could this conversion, so dividing by 1,000, that is a marking point. So this conversion here, so some people still manage to pick up a mark for correctly taking a number and dividing it by 1,000 to convert it into kilo ohms. That's perfectly fine. Right, now D. Explain where a lamp should be connected in this circuit so that the voltage across it increases as the light received by component X decreases. Another tricky question. Most commonly answered incorrectly because I think people try to pick an answer and try to say, I'm going to assume series, and then try to explain it. But there are 3 marks here. Let's first start with what we know about component X and how it behaves, because actually there are 2 marking points just for that. Okay, so an LDR, so component X, okay, the component X, resistance increases when it gets dark. Okay, so we know the light is going to go down, so therefore the resistance of X is going to go up. Okay, what's the second thing that we could therefore say? Well, think about, what's going to happen to this in just this circumstance. We've got 3 volts here, we've got 9 volts here. Now this has got 9 volts, it's got a resistance of 4,500. This has got 3 volts, it's got a resistance of 1,500. The thing with higher resistance takes more of the voltage. Okay, so voltage is used up as things with 12 volts, and we use them up in a circuit. We're using them based on how much resistance each component has. So as X's resistance goes up, this number 1,500 is going to become higher. Okay, eventually, let's take the answer. Let's eventually have it go to 4,500. At that point, this voltage is going to split, and it'll be 6 and 6 when the 2 resistances are equal. If it goes higher, then this will start to get more. So as the resistance goes up, as resistance goes up, then voltage received. I don't think. Okay. What's important is that there's still 12 volts, but this 3 is going to become 6, okay, or 9. Whereas this one will go down. So the first 2 marks are just actually for saying what's going to happen to the resistance of component X, and what does that mean about the voltage it receives. So where therefore do we want to put the bulb? Okay, you can imagine that this is a bulb, it doesn't really matter, but we actually can immediately see that putting a bulb in series, okay, is not helpful. It cannot work if the bulb is in series, because if the bulb is in series with these other 2 components, as it gets darker, this thing is just going to hog more and more and more energy, more voltage. Okay, so but what we want is the bulb to get more voltage as this gets more voltage. So where do you want to put it? You want to put it in parallel, because things in parallel receive the same voltage. So as this thing takes more voltage, the bulb will also get more voltage. So therefore, you want to connect in parallel with X. Okay, so that's sort of the stages of the marks. One for saying how the LDR behaves in terms of resistance, one for therefore saying what that will do to the voltage it receives, and therefore the conclusion, you connect it in parallel with component X. If you put it anywhere else in the circuit, then as it gets darker, it's just going to get less. Okay, so that's how that one works. Cool. Right. Question 5. Circuit diagram for this electrical circuit. We've got the variable resistor, which is actually what this thing here is doing. So what we need to do is draw our circuit diagram. So we've got there's the ammeter, the cell, there's the resistor. Okay, so these things in series, so correct symbols, and it's all a series circuit. And then it says draw a voltmeter on the diagram to measure the voltage of the variable resistor. Okay, so there we go. So that's quite a nice 6 marks. Explain how the voltage across the variable resistor changes if more mass is added to the end of the elastic string. Right, okay, so let's just have a little diagram as to what's going to happen. If we add more mass, this thing gets pulled that way, and so our metal foil is going to move, say, to here. Okay, so what we're going to do is we're going to make this sort of wire, this resistance is going to get longer. So as it moves that way, we're going to make the whole thing longer, which means that this the resistance of this thing is going to increase. So this is like a variable resistor making the whole thing longer. Okay, so what are the marking points we can get? And sort of like there's 4 marks available for any 4 of the following. So do that. So the first mark is that resistance will increase. So the second thing, we can say therefore the it allows you to say either, and that's of the stretchy resistor. It's quite nice. It also says therefore total resistance increases. Okay, so let's say we had doubled this resistance from 5 to 10, and this had a resistance of 10, then we've gone from 15 to 20. So, you know, we just added more resistance. So you can get a mark saying the total resistance, the whole circuit's gone up. It's quite exciting. A reference to the equation in the form of current is equal to voltage over resistance. Okay, so the voltage is a fixed number, it's from the cell. The resistance, the total resistance of the circuit has gone up. So therefore, because of that, we can therefore say that the current in circuit decreases. So if the current in circuit is decreased, the voltage across the fixed resistor must decrease because this has a fixed value of resistance, say 10 ohms. So so V cross okay, and because the voltage across the fixed resistance has increased, therefore the V across stretchy increases because apologies, as total V is constant. Okay, so there's a lot you can say here. There are 7 possible marking points. The stretch resistors increasing resistance. The total resistance of the circuit's gone up. Current is voltage over resistance, and so current in the circuit decreases. I've already put that there because the total voltage is constant, so current is still down. The voltage across the fixed resistor is going to go down because you've got I times a fixed number, and therefore the voltage across the stretchy resistor will go up. So they're like the 7 marking points you could say to explain what's going to happen to the voltage. Okay. Right, okay, then we have a little graph which I'd already drawn, which looks like that. What's the independent variable in the student's investigation? The independent variable here is the voltage. We've got a variable power supply, you can vary the voltage at a rate that you want. And then we've got our graph, which is here. 3 marks, what are your marks for? A suitable linear scale, so you going more than halfway of the grid in either direction. Orientation is not important. So the scale is 1 point. The axis, which is an axis title and a label, that is milliamps, that is volts. And then you have a plotting mark. Okay, so scale, axis, plotting, and then draw a line of best fit, which is a straight line. You should probably use a ruler. Yeah. Okay, cool. Right. Number 6. Got 2 cats, light coloured skin and no fur, thick black fur. Both cats have the same body temperature and transfer energy to their surroundings when they are outside on a cold day. Compare how cat X and cat Y transfer energy to their surroundings. Big immediate misconception that happened in a lot of answers is people forgetting that the direction of energy transfer is out from the cats. Okay, so energy is going that way. These are the warm things. These are the hot things, so they are losing energy. So we have to therefore consider how they are different in terms of convection, conduction, and radiation. So let's consider, well, we know this one's got fur, this one doesn't. This one's black, this one isn't. And it's got light coloured skin. So let's consider our first thing. So in terms of our first point, so X will lose more by conduction or convection. Okay, Y will lose more by radiation. Okay, so this is the 2 things. Okay, so we've got to think, why is this thing going to lose? Why is X going to lose more by conduction and convection? Why is and why is this one going to lose it more by radiation? So let's consider the third thing. So cat Y has fur. Fantastic. So let's think about what fur does. So fur traps air. We could also say that fur is a good insulator, or it's a poor conductor. Similarly, if you go and touch something cold and you wear some gloves, okay, it's going to be, that's what fur essentially is. So fur is a good insulator, fur is trapped air. These are all marking points that you can get. Trapped air cannot move around, and therefore trapped air reduces convection, and there's other things that I'll say. Oh yeah, and also trapped air is a good insulator. So there's quite a lot of things to say about here. Okay, so any air that gets warmed up by being next to cat X, just boom, straight off, because there's nothing that's keeping it there. So This is what the fur is doing to keep the cat white warm. However, on the other side, what else can we say? Is that dark surfaces are better emitters of radiation. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So 8 points. I've missed one. Oh yeah, larger surface area increases conduction. Large surface area increases conduction. I am going to consider that. Okay. I'm gonna know why that is. Okay, so there is another point here, which is written in the mark scheme that I just read. And said larger, so larger surface area. That is a very, very badly worded thing. But that is to do with the fact that so the actual skin, okay, the body of this is the thing that's warm. And if you've got a collection of fur, think about how much skin is directly in contact with the floor. Well, for cat white, it's just the little cute things on its paws, the little lumps. Everything else is covered by fur, so there is no direct contact. So the surface area of this cat in direct contact with the floor in terms of exposed skin, very small. This, all of it, so everything that's touching it. So that's the comment about the conduction and the surface area. No marks at all if you refer to absorbing of radiation, because this is all about emission. Okay, so there we go. That's what we can talk about there. Right, question 7, some pistons. Right, okay, so hydraulic lift. Calculate the pressure difference from the bottom of the piston and the bottom of the oil. We've got a 57 centimeter height. So we want to use the pressure difference is equal to rho times G times H. So there's a mark for density times gravitational field strength times height is 1 mark. So that's 1 mark there. There's another mark for recognizing that height is 0.57 meters. Okay, rather than it being 57 centimeters, because otherwise you get a power of 10 error. So therefore the pressure difference is density. So we've got 820 times 10 times 0.57, which gives 4,700 to 2 significant figures. Okay, there are nothing penalising you for significant figures here. If you see a power of 10 error, then it's because you've left it as 57. You'd get 2 marks rather than 3. A 24 kilogram mass is placed on piston X, so put it there. Calculate the weight of the 24 kilogram mass. Give the correct unit. Because W equals mg is a very common thing, the first mark is for literally just for substituting it in. So W equals 24 times 10. So that gives us 240 newtons. Is your final mark. Right. So substitution. So 1 for substituting in, 2nd for evaluation, 3rd for the unit. Calculate the extra pressure on the oil due to the mass. So we want to use pressure equals force over area. So we substitute that in. So we've got 240 over an area of 1.2. So we get 200 pascals. So 1 mark for substitution into the formula, 1 mark for evaluating. The oil transfers the same extra pressure to piston Y. Calculate the force acting upwards on piston Y due to the extra pressure. Okay, so here, okay, we've got to again substitute pressure is equal to force over area. So we substitute in, we've got an extra pressure, so it's this number that we're using here. So we've got 200 is equal to force over area here is 4.8 meters squared. So therefore force is equal to 200 times 4.8, and therefore we've got 960 newtons. Yeah, this is how hydraulic pistons work. A small force over a small piston can be transferred to make a large force over a larger piston. Okay, so there were no marks given for formulae, so it's a bit mean if you forgot one of these formulae, particularly if you messed up pressure is force over area. So piston Y starts to rest, rises slowly, then comes to rest. State how the following energy stores have changed from before the motion to after the motion. So goes up, goes down, stays the same. So piston X is going down, so the GP of potential energy of piston X, that has gone down. GP of piston Y, that has gone up. Chemical energy of piston Y, there has been no chemistry, so that has had no change. Kinetic energy of piston Y starts at rest, comes to rest. So even though it moved in the middle, but by the end of it, there has been no change. And then we're on to the final question. So we've got a dog sitting on a water-filled bag to keep cool. Got some data about the dog. Dog sits on the bag for 22 minutes. Calculate the energy transferred from the dog to the water by heating 22 minutes. So, although there is some information that's lower in the table, that's here and here, the only thing we are that is of interest to us in this first question is this bit. Okay. The rest is not something that we need. Okay, so they've given you all the data you're going to need for a whole question, but you only need this bit now. Okay, so excuse me. So we want to say, so dog sits on the energy transferred. We want energy is equal to power times time. So that is 75 watts times by a time, which is 22 minutes. So we've got 22 minutes. We've got to multiply that by 60 to turn it into seconds. So there is a conversion mark. There is a rearrangement, rearrangement substitution mark, and the final mark is for the evaluation. So you get 99,000 joules. State an assumption you have made when calculating the energy transferred. So we are assuming that power by heating in what? You can't just say 100% efficient or no energy lost. There needs to be a little bit again of being specific. So we would say that the various things we can say, and there's a lot really that are listed in there, and I can't write it all there, so I'm just going to write it to the side. Acceptable things that they asked here is that the temperature of Doge, it's not Dogecoin, temperature of Dog is constant. You could say the power is constant which, you know, over 22 minutes, that's quite a lot. So no heating of the outside. So that's no heating of the, you know, so the actual the bag itself. You know, we've got to heat the bag, and this is all in there, assuming that we've gone to the water, and no heating from surroundings. So that is the bag. And also no heating of surroundings. Okay, so we've assumed that this has all gone into the water, and actually that's quite a bold assumption for 22 minutes, but there we go, those things. And so once we've got that, so any of those or anything's kind of along those ideas, but as long as it doesn't just say 100% efficient, because, you know, it's not a designed process. Calculate the temperature of the water after 22 minutes. So we're going to use the equation Q equals mc delta T. So we want to work out the change temperature, but let's put in our amount. So we've got to take our energy that we've had from here. So you can get an error carried forward if you carry this number, if you did this wrong. So we've got 99,000 is equal to 8.7 times 4,200 times the change in temperature. So we can therefore get a temperature rise is equal to 99,000 over 8.7 times 4,200, and that comes up as being 2.7 degrees Celsius. Okay, so there's 1 mark for that, 1 mark for this, 1 mark for that. Final thing is got 2.7 degrees, but that is a temperature rise, so we've got to add it to that one. So our final temperature is 16 plus 2.7, which would be 18.7 degrees, or 19 if you're rounding. And there we go. That was the exam. Hope that has been of